If you've spent any time in the big data world, you know these two names, Apache Spark and Apache Flink. For years, they've been the heavyweights, the go-to choices for processing massive amounts of data.
It's a classic showdown, right? It's the debate that's been happening on blogs and in conference halls for ages. Do you stick with Spark, the undisputed champ of batch processing? Or do you go with Flink, the master of real-time streaming?
But this isn't going to be just another versus explainer. Because what if I told you that a brand new challenge is emerging? One that's so massive it's forcing a complete rethink of how these systems are even built. The whole game is changing right under our feet.
I mean, this quote really says it all, doesn't it? The sheer amount of data today is just overwhelming. And our tools, well, they have to evolve to have any hope of keeping up. So to really get where we're going, we first have to understand where we are. Okay, let's dive into it. So let's kick things off with the absolute core difference between these two. It really all comes down to their philosophy, to how they fundamentally see the world of data. And here it is, the crucial difference. Spark, even when it's pretending to stream, is all about micro-batching. Just imagine a continuous river of data getting chopped up into tiny little buckets. Spark processes one bucket, then the next, super fast. Flink, on the other hand, was built from the ground up for true stream processing. It looks at each single event, one by one, as it flows in. That's why it's always been the king of low-latency applications. All right, let's pop the hood and look at Spark's architecture. You've got your master node, the driver, which is basically the brain of the whole operation, telling everyone what to do. Then it sends out all the tasks to these worker nodes, called executors. The magic ingredient here is something called a resilient distributed dataset, or RDD. Just think of it as a really smart, fault-tolerant collection of your data that can be worked on in parallel across all those different machines. And this setup is what gives Spark its legendary strengths. Its in-memory computing makes it blazing fast for those big batch jobs. It's got this incredibly mature ecosystem with easy-to-use APIs and powerful libraries for pretty much anything you can think of, from machine learning to SQL. It's a versatile beast, no question.
Now, let's switch gears and look at Flink. You'll see it also has a master worker setup, but you can tell right away that its parts are purpose-built for a never-ending flow of data. You've got a job manager acting as the conductor and task managers as the workers. The whole design is just streamlined for a constant, non-stop stream.
And this is really where Flink shines. It gives you that true, super low-latency streaming. It's also a monster when it comes to stateful processing. That just means it can remember things from one event to the next, which is crucial. And it does this with rock-solid exactly once guarantees, so you never lose or double-count data. Plus, its advanced windowing is perfect for spotting complex patterns over time.
So for the longest time, that was the story. Spark for batch, Flink for streaming. Pick your poison. But then, the scale of data just went vertical, and it started to expose this hidden, fundamental flaw that actually affects both of them.
Get ready for this number. 4.4 times billion transactions per second. That's not a typo. That is the insane peak data flow that Alibaba's Flink systems had to handle during their big shopping festival. And when you get to that kind of cloud scale, even the strongest architectures start to buckle. So what's the problem? It all comes down to this one concept: coupled compute and state. In the old way of doing things, for both Spark and Flink, the processing power, the brains, and the data storage, the memory, are stuck together on the same machine. It's like having a smartphone where you can't get more storage unless you buy a whole new, faster, more expensive phone, even if you don't need the extra speed. And this chart just lays out the waste so perfectly. According to Alibaba's own data, 35% of their jobs are disk-bound. That means they are forced to buy more and more expensive compute power, more CPU, just to get enough local disk space for their data. It is wildly inefficient and gets incredibly expensive fast. And this coupling, it just creates one headache after another. Suddenly, the size of your local disk is a hard limit on how much state you can handle. Background jobs start fighting with your main processing tasks for resources, causing weird performance issues. And the absolute worst part? If a machine fails or you just need to add more capacity, you have to physically copy mountains of data from one machine to another. It's slow, it's clumsy, and it's expensive. This is the exact problem that Flink 2.0 was born to solve. It introduces a totally new way of thinking, a revolutionary architecture that decouples compute from state. So how does it work? Well, it's pretty brilliant. Instead of keeping all that important state data on the local machine's disk, it puts it on a shared remote file system that everyone can access. The local disk, it just becomes a speedy, optional cache. So now, when you need to scale up or recover from a failure, there's no massive data shuffling. The new machines just connect to the shared storage and get to work. It's like giving your phone unlimited cloud storage. You can upgrade the phone and the storage completely independently.
And the results are, well, they're not just a little better, they are staggering. Take a real-world workload. The old Flink needed 16 compute units just to get enough disk space. Flink 2.0, it ran the exact same job, no problem, with just 8 units.
Yeah, that comes out to a 50% cut in operational costs. Just let that sink in. By simply separating compute and storage, you completely get rid of that need to overpay for resources you don't need. For these jobs, you're literally cutting your cloud bill in half.
But the savings aren't just in your wallet. They're in time, they're in agility. I mean, just look at this chart. The tall bars on the left show the old way. Things like moving a job or scaling out to handle a traffic spike took minutes. Now look at the tiny little bars for Flink 2.0 on the right. Those same operations now take a few seconds.
Let's put a number on that. For job migration and recovery, Flink 2.0 is 16 times faster. In the real world, that's the difference between a minor hiccup that no one even notices and a major customer-facing outage. And if you thought that was impressive, check this out. When it comes to scaling out to meet a sudden surge in traffic, the improvement is a mind-boggling 49 times faster. This is elasticity. This is what being cloud native is all about. It is an absolute game changer.
So, why does all this matter so much? This whole shift from a coupled to a decoupled architecture, it's about way more than just Flink.
This isn't just another product update. This is a preview of the future for all cloud-native data systems. This idea of disaggregating compute and storage, it's quickly becoming the blueprint for how you build efficient, scalable, and cost-effective systems in the cloud. It's the flexibility that the modern data world has been screaming for.
And that really brings us to the final fascinating question. Now that we're solving this huge architectural bottleneck between compute and state, it really makes you wonder, what's next? Now that we've broken that chain, what's going to be the next great challenge that forces our data systems to evolve all over again?